Okay, we're going to start. I have to say, this is one of my favorite subjects of all time. And why? Because it brings a couple of things together that I love: economics, analytical mechanics, and geometry, and especially differential geometry. So, you know what geometry is? Differential geometry is the geometry of very small movements. Okay, I'll get into that, but it's a fairly modern development in mathematics. And it really came out of analytical mechanics. So, analytical mechanics is a different approach to mechanics than Newtonian mechanics. Last year, we went through the lecture series of how to do the theory of demand and economics with Newtonian mechanics. And here I'd like to show you how to do it with analytical mechanics. Now, analytical mechanics was started by Lagrange a long time ago, hundreds of years ago, and it was first seen as a curiosity. So early in the 20th century, there's a famous physicist and philosopher called Ernst Mach, and he says, interestingly, that the contribution of Lagrange in mechanics, and that's part of analytical mechanics, is one of economics only. Now, what he means by economics is not what we mean by economics, namely the subject about money and goods and all of that, but it is about being frugal, right? Having a nice way of saying things. But he didn't see any other possibilities. Then come the 20th century and Einstein, and everything changed. So Einstein, he extends Newton's laws with application to relativity and also to quantum mechanics. And none of these were solvable by what became known as Newtonian mechanics. All right, so although Newton's formulation was slightly more general, this is what we still teach here in mechanical engineering. And a lot of problems became only solvable with those new methods. Well, you know, the movement of light, things going at very high speeds, you know, close to the speed of light. Also quantum particles that have no mass, like photons. They were only possible to treat those like this. The theory was very hairy, and it was cleaned up by mathematicians using differential geometry. And then, you know, things like Maxwell's laws and other things that were 16 equations or 32 were all condensed down to one simple equation. And there was a whole wave of doing things geometrically. And what they mean by geometrically is not only that it's like geo, which is earth, and metry, which is way of measuring. So intuitive way of thinking about it, because we all live on this earth and we'll all be measuring how many steps it takes to do this or that. But it was also a way to get away from all the subscripts and superscripts and matrices and all of that. And all of this was kind of irrelevant notation and go back to the essence of what's going on, what was purely physical. And this is a very beautiful construct that came out of here, all put together. And it really hasn't gone into the curriculum in a typical engineering school. Maybe the physicists do a little bit better, but I also feel that, you know, it could be used a lot more. Now, one of the things that goes wrong is that this is taken over by the mathematicians. And although it came out of mechanics, you know how these guys are. I mean, they take something, they start proving theorems, and you can buy a book on differential geometry that's this big with not a single picture in it, right? Okay. This is very hard for us engineers to deal with. Yeah, I mean, and that's one of the things is preventing us from really using this, okay? The other thing that's preventing this whole business of analytical mechanics to use that in engineering is that it really, up to now, doesn't really include friction very well, the friction forces. Within this group, we've been making different types of progress to fix that. And that's also one of the reasons that I feel friction is also very important in economics. And now you have economic friction everywhere. So I feel this is really the right place to start now, to start teaching this and make part of the curriculum. Now, when this kind of stuff gets taught in a mechanics course, it just feels like really abstract, okay? It makes no sense, you know, particles minimize something called an action, or some kind of theorem says that phase-space volume is conserved. That's the Liouville theorem. All kinds of stuff. And then they talk about a tautological one form, and it all becomes so abstract that you kind of lose touch with what's going on. Now, one thing I want to convince you with is, and I think at the end of several lectures, you'll find, at the end of this lecture series, you'll know that the situation is reversed for economics. That this is the way it is the most intuitive, okay? So remember when we did the Newtonian price, how did we define price? It came out of thin air, really. We just said price is the thing that you have on a demand line, P and there's M times V, and boom. That was also a bit of the problem with Newtonian mechanics. Momentum comes out of thin air, okay? Okay, Newton did a great job by defining a force, our incentive, as the time derivative of momentum, as the flux of momentum. But if you don't really know what momentum is, then, In analytical mechanics, or especially Lagrangian mechanics, momentum is a partial derivative of something, okay? How does that help? Something else is even more complicated. But we'll see that that something is the running cost. So the price, the analog to momentum, will be the marginal running cost if you buy an additional unit. Now, that's precisely the price, okay? So all these abstractions become the most natural thing. And furthermore, once you see that this is the case, you would think, well, there's no other way to do this, really. So there are some competing theories on how you have economic forces and economic prices. But I think you'll be convinced after this lecture series that this is the only way to do it. And analytical mechanics will convince you of that, okay? It does something similar to mechanics, because I think it was Einstein who noted that photons have momentum, but photons have no mass. Now, how can something have momentum but no mass if P is M times V? If M is 0, then obviously that's, Well, M is not really 0. M just doesn't exist. So what is P is M times V? All right, it's a very complicated issue here. All right, okay. So if you then use analytical mechanics, there's no problem. You just have the right Lagrangian, and you take the right derivative, you get momentum. All right. Similarly, we have things that we have situations where the price elasticity of inelasticity is undefined. Okay, when you're perfectly inelastic, it's undefined. Okay, infinity, I don't know what that is. All right, so still you may have a price. You can have any price whatsoever. You're perfectly inelastic. So the Newtonian thing will break down, but this thing will work. We'll see. It's very important. Okay, to get the price of money, other kind of things. All right, so that's my preamble. Okay, so this is a wild ride. I'm going to try to bring all this stuff together. And what I'm not going to do is do differential geometry for dummies. I'll start drawing vectors when it's covectors and saying matrix when I mean tensor. Okay, so I'm going to use all this modern language and these modern things, but I'm going to do it in a way that it remains intuitive. I'm going to stay away from all the theorems and this, and I'm going to try to put back the geometry into geometry, okay? And really just make pictures of it. That's the way we think about it. Mathematicians don't do that. When they say vector, they have an object. When we say vector, we see a line with an arrow, okay? That's what I want to keep to, okay? So, but we're really going to do the real thing, all right? And that's what I want to do. And the same with analytical mechanics and economics. Well, we're not economists, so who knows? But the program here is to see how well this fits into there, not whether this can be fitted to here some way. All right? Okay? So we're engineers. We're going to stick with what we know, which is this, and we're going to see how well we can describe economic systems with this. Okay? All right. So with this, I'd like to go to my first slide and just spend a little time before we attack this business of being a little bit more, expansive about this difference between the Newtonian approach and these other approaches, okay? Because everything is going to feel different, although it's going to end up doing the same thing, okay? Now here is the typical, setup we have, that we're familiar with. We have the demand, that's the mass, and that's an inertial element, some body, and the mass is the price inelasticity, okay? The forces are the incentives, they're working here, and they all balance out, and the change in the price, is determined by the storage incentive, which is that convenience, and the frictions, economic frictions you have to overcome, okay? That's the kind of stuff we're talking about. So we're talking about all these incentives, and we balance these incentives, to get the resulting demand, which is just some vector that we draw on there. This is a typical engineering type of thinking. So it's a very schematic approach, okay? And I say it's this balancing. Why? Because you make these free body diagrams, and what do you make them of? Well, of forces or incentives, okay? And the whole thing has this incentive-driven kind of thing, but there's really no geometry other than that you draw, a vector as a velocity as some kind of vector like this, okay? All right? Now, here on the far left is the Lagrangian approach, and here is the Hamiltonian approach. And these are the typical pictures. So it's very, very different. So what do you do in a Lagrangian approach? Well, you have, here there's one good, right? And you can measure this distance, and that gives you the amount of this good. Here you could also have one good, but the pictures don't make much sense, so I put two goods, two commodities. And I say, okay, we have some agents, and he starts off here, and he has so much of good one and so much of good two. And then he starts buying and selling. I think this guy's only buying, but whatever. And then he ends up over here at some point in time. So this is some initial time, this is some time t. But he's got to go all the way up to there, and that's his final time, right? So we draw his activity not in terms of something that may be moving, but as a path, sort of a journey. It has the idea of a journey, and this agent navigating this stock space, as it were, okay? Now you can say, okay, that's the position. What happened to the demand itself, the flow? Well, we all know that's just the directional derivative along the path, right? So you're indexing this by time, and then if you go fast, there's a big vector. If you go slow, there's a small vector, and it's a tangent factor, okay? So we think of this as a tangent vector. So we think of the stocks as a point and the flow as a tangent vector at that point, okay? A very different picture than here, where this was the demand vector, and this is it, all right? Okay? And then whatever all these things are, we don't know yet. Somehow, somebody has to tell us so that we know how fast we're moving along and how this demand is changing, all right? Okay? Now, the way we do that is we say, well, maybe he could, I took this black path, and this is apparently what he did, but it could be that you take another path, like this red one, or this orange one. I call these things courses of action also, because it's really a corso means, of course, in Latin, a path, and action is just your activity, what you've done, what you've been buying, right? But the course of action you can view as all right? So he could have done this, and he could have done that, and he could have done that. You're just kind of imagining all these things you could do. And out of those, you want to take some cost optimal one, right? So you're going to do some kind of cost-benefit analysis. So there's some cost associated with some negative costs. These are benefits. You're going to trade them all off for each path. And then you take the one that is the best, right? However you do that, I don't even know, but we do it all the time, right? You plan a trip to go somewhere, you consider going through Belgium or Germany, I don't know, you go to your winter sports vacation, particular time, you know, you go fast here because there's no speed limit, and in the Netherlands, you got to go real slow. You try not to tank up too much before you hit Germany or Belgium, you know. Huh? You stop immediately. So you somehow you got this whole thing all sorted out, and you know, huh? Okay. So it has a feeling of navigation, you know. Okay. So you're gonna choose the one that minimizes the total cost, and you're gonna take this one, you know, some kind of best path, the shortest path in this weird world where you have costs everywhere, right? And of course, that's part of the kilometers you're making because you have to pay per kilometer, but you also have to pay a toll, either this, so it's a little bit more complicated, all right? So there's some world, and you take the shortest path in that world, and the mathematical name for the shortest path in some world is a geodesic, all right? So just in Euclidean space, when there's nothing hampering you, it's a straight line. But on Earth, it's a great circle. You know all this, right? And this weird world, it may be something else. Okay, so this approach is very different than that. You see, it's very natural. It's cost benefit. This is what you do. Huh? All right. You're going to minimize total cost. Okay, who's going to argue with that? Nobody, right? Huh? As long as you define this correctly. All right. Huh? And you imagine, you know, taking all these different courses of action, and you choose the best one. All right, nobody can argue with this approach. You can argue with this approach. That looks ridiculous. And you're surprised how well it works. Here, you know it's going to work. You'll just be surprised that you can make it work because it seems so complicated, right? That's a problem. See? Now, there's another way to go from this picture to this picture. Okay? Huh? And it looks completely different, but yet also this is geometric. Now, this is a Hamiltonian approach, and you replace this whole picture here with minimization and passing with something which in engineering is called, we would call in mechanics, the energy. All right? Now, what this turns out to be is the surplus, the economic surplus. As you know, energy, kinetic energy is the economic surplus. So is potential energy, because you can change it to kinetic energy, which is surplus. All right. So these kind of systems, they conserve something called surplus. All right. Now, in analytical mechanics, they also are seen to conserve something else, which is action. There's somehow a piece of area of this phase plane that's right here is one, dp dq, right? So what is that? Now that's a little bit of a price. So let's go first to this. This is, I drew it. This is okay, second order system. So really it's this system. I took away the friction. Here's momentum. So that's the price, right? Here's the stock. That's this distance. That's the price. And this thing is going this way, right? It's trading in high prices, high stock levels, low prices, low stock levels, and it's going on like that. We all know this, okay? This Hamiltonian, or this surplus, that decides how fast this is going, okay? And it's going at, and this thing is conserved, so it's kind of going at some kind of weird constant speed. And there's a little bit, and this area here looks like it's conserved, okay, in this motion. Now this area has units of P times Q, which is units of value. So there's some amount of value that seems to be conserved here. And it's made up of two things. You can see it either made up of all these little bars put together, right? So you integrate this out. So you multiply the price by a small change in the stock. That's easy enough to imagine, right? So you pay so much per item, and you bought an additional item, so that's just, you know, that's just your cost basis, right? That's what it costs you. That's what we call the cost basis, right? You can take, you can also look at this little thing. That's also easy enough to imagine. That's when you go in a little square like that. You increase the stock. You margin up the price. You sell it again. You margin down the price, right? And you're back to where you started, right? So that's a little piece of value right there. Okay. So these are concepts that will come. This one. The interesting thing of this one is, like here I can make it infinitesimally small, but if you don't, you'll have something like that, and that is equal to Planck's constant. So you see Planck's constant emerges here as your smallest unit of value. You see, this is how it's a little bit more general, okay? Okay. Anyway, this whole thing is about conservation of properties, conservation of energy, conservation of value, or phase space volume, and things like that. All right? It's slightly more abstract, but it gives a picture for economics, which is very much like the picture of making a profit when you're in a company. All right? So you want to conserve these profits, and taking different derivatives of your profit or your surplus, you'll get what you're demanding and what you're doing. This, we'll see this. All right, so it's very natural description for economics. Not so easy for the consumer as this, but this is more of a way a firm would look at it. All right, but both are valid pictures. Now, this is a lot of researchers recently gone into this. People have looked at symmetries and invariances of this thing. So we'll make a lot of this, okay? But here's where we're going to start. This is the easy thing, all right? Conceptually. Then we'll move on to this. We'll interleave it like that, all right? And then we'll go and solve some problems, okay? So just to summarize, you see this whole thing, this is really very geometric, huh? Now this is more of a schematic thing, right? Huh? That's why the title is indeed here, Differential Geometry, Analytical Mechanics, and Economics, okay? All right. So there's a bigger picture here. We're going to have quite a few lectures. Only this thing will take us through 4 or 5 lectures, so it's easy to get lost and think like, okay, huh? But I just wanted to lay that down. All right, huh? And then at the end of it, we'll, or in the middle, we'll show how effectively this is the same as that. All right, doing this. In fact, from this minimization comes the Euler-Lagrange equation, and under certain conditions, that's equal to Newton's equation for this thing. All right, huh? And same with Hamilton's equation is a reformulation of Newton's equations. All right, so from a very different perspective. And my understanding is that, yeah, you just understand it that way. The problem is, in other versions, I would do this first, and it would just be all understandable, but too abstract in order to turn around and then solve a problem. So the other approach, you can just go ahead and build your multi-put and start just doing stuff without having to understand the whole thing 100%, which is the way engineers work, right? First, you have to be able to do stuff, and then you will get motivated by understanding it a little further so you can do more, right? Huh? All right. So let's go. This is the Lagrangian approach, and this is one big slide with all the ingredients, okay? And I just want to step through that. So there's 3 things going on here. There is time itself, so that's important. This is a dynamic theory, okay? Most economic analysis don't include time. They'll all talk about equilibrium and what stocks are, what flows are, what this are, this. Here, there's time explicitly in there, okay? So economists will also use Lagrangians. Time is not really, it's more about equilibrium and finding minima, but time is not part of it, huh? For the most part. The middle is all the economic reality. Those are the economic states, all right? I'll explain exactly how it is. This is some abstract thing that's out there, right? You don't even, there's no coordinates drawn on this. We only know what the dimensions are for now. Huh? Here are the dimensions with 2, and I'll explain how you get there. Okay? So think of the economic reality like you think of physical reality without the coordinates. There's just this room. Okay? Now, if I say, where's my laptop? It says, well, here. You know, well, you can say, I don't know what here is. And you say, okay, I'll put a coordinate system and I'll measure this one and I'll measure that one and this, or I'll do polar, and I'll make all these choices of which nature knows nothing, right? Okay? That's what you have to understand here. This is only the things the economy knows about or nature knows about, okay? None of the choices you make on how to measure it and how to index it, okay? This is an important distinction, you know, because, you know, we draw a vector as engineers like this, but just as easily, if I ask somebody what's a vector, he will give me a column of numbers, you know, huh? Vx, Vy, is something like that, right? Huh? What is a vector? Is this the vector or is this the vector? No, this is the vector, and this is the representation of the vector in an x, y, z coordinate system. All right? Huh? You got to keep the two separate. All right? The vector is what it is. Your velocity is what it is, independent of how you measure it. This is an important distinction that was made because of Einstein's theories. There were people that came along, like Ricci, I believe, and others, you know, that says, well, the whole thing is just getting so complex because we got all these indices because we chose all these coordinate systems that we're so used to because everything was easy, and it now everything becomes really hard, so we don't want to do this anymore. So they were able to formulate everything in this coordinate-free manner, all right? So this is how you have to think of this economic states, okay? So the state space is now not some long column of stuff, it's just the thing itself, all right? Okay? Then here on the right is something that you would call a coordinate chart, all right? And it keeps track of everything that's going on, all right? So those are the 3 ingredients. So in economics, this is going to be a set of statements. So a set of statements are like Excel sheets or whatever you have, or, you know, we like to draw graphs, but business people give these little Excel sheets or whatever, where you give the values of this and the value of that, and, you know, huh? Okay? But I prefer this kind of thing. So this kind of way of keeping track with coordinates is what you would call bookkeeping. You know, what accountants will call bookkeeping. So these are his books. And the books contain all these ledgers, they call them sometimes, or statements, okay? All right. So those are the 2 activities. So you see there's the executive phase. This is what the CEO does, as chief executive officer. He says, we'll buy this, blah, blah, blah. What is what you do, right? And this is what your accountant does, and your bookkeeper, and your bank, all right? And this is your great or awful reality, all right? Huh? Okay? Now, let's move on. Let's see what I have here. Okay. Now, let's start with this stock space right here. All right. So how many stocks are there? Suppose I have an agent and I have D commodities or D goods. Well, I'm going to have a stock space of dimension D, right? Suppose I have N agents with D all trading in these D goods. How big should the stock space be? Well, I have to multiply D by N because each agent has a full stock space that I need to keep track of, right? So for each agent, I have a complete set of books in my bookkeeping, all right? So my total degrees of freedom is the product of my number of agents times the number of types of commodities, all right? So it could be a big space, all right? But this is what you start out with. You have to start out with a total space. Here, that's not the case. In Newtonian mechanics, you start with one, then you add something else, then you add a third one, then you run out of dimensions. So what am I going to do now? I don't know. I may make something else. I don't know. You know. Here, you just first list what are my agents and what are my... So it's a kind of more of the whole system at once. Okay? All right? So that's just this space. Now, I drew this as kind of a weird, funky space, and later on I'll give you examples for when it's flat and when it's curved and which way it curves, all right? But just go along that this is just a space of points that is in some way structured. So you gotta also realize it's not a vector space, okay? What is a vector space? We always think of everything as a vector space, but that's not the case. A vector space has to have a zero, and it has to be that something that's 3 times this, you know, you can distribute the linearity. So where's the zero? What is a zero stock level? Well, nobody really knows. This is something you choose, right? Huh? Okay, you can go negative, positive, you know. Huh? So there's no zero. There's no way of multiplying them out, you know. Naturally, in all cases. Some specific cases, yeah, I'll come to that, but not in all cases. So this is not a vector space. It's just a space of points. But the points, there is a sense in which they're close. You know, that's what we call as a topological space. And there is a sense of making a movement and acquisition that I go from one to the other in a very, you know, small difference. That makes it into something that's called a manifold. Okay? Variëteit in Dutch. Okay? So we'll assume that. You'll see all these examples that's the same. And if it isn't, then yeah, forget about it. But it is. You know, it makes sense, right? You know, if I have 5 gallons of gas, I can get 5.0001 gallon of gas, theoretically. Maybe not practically, but theoretically. All right? Huh? Okay, huh? So I can get these things arbitrarily close. Huh? All right? And I can kind of go smoothly from one to the other. I don't get boink. Huh? There's a whole big hole in. Huh? All right? Huh? So this is my stock space. All right? Huh? And I have these number of agents and these directions. They're all different types of goods and services. All right? Now, here's already one thing. Now, what is then the tangent vector to this? So, okay, stock space. Then we have time, and what is now the path, the course of action the agent does? Well, at t initial, he starts off here, right? Huh? And as time passes by, he goes, so these are all like units. Maybe he goes a little slower, and then he goes faster, right? Huh? You see that? Huh? This is a typical trick mathematicians do. It's like you would say, what is a path? Well, as an engineer, you would say, well, I'll just draw it on there, and that's a path. And then I'll just index time. But how do you do that rigorously? You know, and you say, okay, I'll define a function that maps the time axis into this manifold, right? So that's the course of action. I'm going to call that alpha. And it's a function that takes your timeline and it maps it into this stock space. Okay? That's what you do. That's what this thing is supposed to do. All right? Huh? This is some course of action alpha. All right? Is that clear? All right. Now, time marches forward at what rate? Well, the rate d dt. This is just a little vector. Forget about the fact that I'm not differentiating anything. It's just the d dt. Okay, that's the way they write a vector, or a unit vector. You'll see later why that makes a lot of sense. Right now it looks like somebody forgot to put something here. Huh? Well, because you did, because you're going to put the alpha here, and then this thing will be d alpha dt, so it will be the directional derivative of, okay, so it's a little trick tool. So what happens is, this is called the push forward. So you take this thing, and then you say, well, here I was there, And a little bit further, I'm going to be there. And if I shrink it down, I'm going to get this, now this vector will map to that vector. Okay? So if I can push forward these points, I can also push forward pairs of points. And then I can also take the limit, and then all of a sudden, plop, here I have my flow, right? My demand vector. Okay? But I'm dividing by time. So this thing, if I plotted it in the stock space, it's going to be infinitesimal. It's going to disappear. You're not going to see it, right? So what you need to do, that thing doesn't even live in the stock space. It lives in a different space, and it lives in its own space of tangent vectors to the path. So this, at every point, you have a new space in which all these tangents, so the tangent vector could be this. It happens not to be. It could also have been this, if that thing was, it happens not to be. All right, so at this point, you have all these options of going. What does that mean economically? All that means economically is that if you have at this stock level, you have all possibility. You can start selling like a maniac. You can sell this one and buy that one. You can do anything you like, okay? And that, what you do, is a separate space at each stock position, okay? And this is the space of all, if you do something, you're going to have this path, and you may have another path, you may have another path. And the space of all these possible tangent vectors to all possible paths is called the tangent space. Okay? Makes a lot of sense. But it's a different space. Okay, so this is something we do explicitly, implicitly in engineering. You'll say, okay, here's my positions. Here I am, and here, puff, this is how fast I'm going. And everybody says, well, you can't really measure this speed here because this is in, say, meters, and this must be in meters per second. So, it doesn't even make sense. You got to imagine there's another space lying on top of it where everything is measured in meters per second. Okay, and where this thing actually looks really big. We do this without thinking all the time. And because all our spaces tend to be flat, now, that's not the case, but now we get away with it. All right. Okay. So there's two spaces. There is this space, which is the stock space. This is also known as the configuration space. Okay. And then there is this space of possible tangent vectors of flow or demands or income if it's money, right? And that is the tangent space, all right? That's called, I'll call it flow space or tangent space or, okay? And that's my economic reality. So there's only two things I do. I have stuff in storage, or I bought stuff, and I'm buying or selling stuff, okay? That's it. I have stuff, and I'm acquiring stuff. That's all I'm doing, all right? Now, you can ask yourself the question whether you're also not changing the rate at which you're acquiring stuff. Well, of course you are, right? So should there not be another space with accelerations on here? And the answer is no. Why it's no, all goes back to a basic assumption that's going to be built in, and it's sometimes called Newton's assumption, but that if you know position and velocity, you're basically done because the forces will tell you what the acceleration is. All right? You'll leave it to the forces, that is the incentives, to say how you're changing this. Okay? All right? So you don't need to have a separate space where they happen to be. You don't need that initial condition. You just need these two, all right, to have the full state, economic state. All right? You're comfortable with that, I know, but it will also apply to economics. And that's the whole, that's the whole analog is going to make that work. All right? So this is all we need. Now, if I say, oh, it's still a lot, right? For every agent, you got to know all this stuff. So it's a ridiculous amount if you have the whole world. So we never do. But if you look at any mechanical system, this is also ridiculous if you do that for every point mass and everything. You got to simplify it down. All right? Huh? So, huh? But this is the number of states. Okay? Now, I already said this is very abstract, right? Huh? So, and here I already put on some units and all of this. What does that mean? Well, that means I'm also saying there's some way I have to measure the stock. In some way, I have to measure or record your demand. You know, how much you're buying, how much you're selling. All right? Huh? And that is this whole business of the bookkeeping that does that. So for every point in this big thing that includes the stock position, but also how much you're buying and selling, I need to describe this by some coordinates, okay? Now, in economics or finance, you don't talk about coordinates, you talk about accounts. So if you want to, if we use a coordinate to measure the length of something or the position, and they use an account to look at the balance, right? Okay? So this is what you got to see. Huh? So the position, huh, is the same, you know, that's the stock position. And the balance in an account tells you how many, if you have the Apple account, it will tell you how much apple's in there. All right? If you have some money account, it will tell you how much money is in there. And you can choose these accounts you want. You can also have the fruit basket account, you know, and then it will have apples and pears in it, or baskets, or other, you know, other baskets, you know? Huh? All right? Huh? That won't change the economic reality, okay? Huh? So you can have baskets with even apples and pears and baskets with twice as many apples and pears, and then you can still figure out exactly how much you have, right? If these are independent coordinates, all right? Okay. Either way, you choose these accounts. So this is a Q1 account and Q2 account. And then you look at this chart of accounts. This is what accountants call a chart of account. I'm using the term in a way more general sense. To take any stock position and just say, okay, this much of Q2 I have and this much of good one I have, right? I have a Q2 amount of good 2 and a Q1 amount of good 1. All right? Had I chosen a different account, these numbers would have been different, right? Huh? If I had two different kind of baskets, it would all have been different. All right? Huh? Now, what do I need to do with the demand? How much he's buying? I have to get some chart of accounts for the flows. Now, what I'll do is I'll line them up with these balance accounts. So I'll say, and this is a separate chart. It's called a flow statement. So a cash flow statement would be, if you have a balance sheet, will be in accounting is the balance of the money you have. All right? And a cash flow statement will be how much is flowing per unit of time. All right? Which you can integrate and then book into this thing. This is exactly this process. All right? Huh? So this flow statement, that's the velocity space that we just kind of plop on it as engineers. That is called a flow statement. So cash flow statement, or this flow statement, inventory flow statement, I don't know, huh? Whatever you want. Okay? So these I make blue, and the stocks I make black. All right? And the process of keeping track what's in all these accounts, this is what's called bookkeeping, right? So now you see the whole picture, what's going on. Huh? So you have your economic reality. You are deciding what to do in time, right? We're doing dynamics. Huh? And then you're keeping track of what you've done right here with your books. And I don't know how you do that right now with your all kinds of devices you have nowadays to do it. Huh? Keep track of what you did. All right? And what you're doing. Not what you did only, that's your position, but what you're doing right now. Okay? You can measure how far you've traveled in your car. It has a separate kind of counter for that. And how fast you're going. It has a speedometer for that, right? Huh? You have both. You know how much money you spent? Because that's derivable from your bank account. And you know how fast you're spending it because you're looking at it flying out. All right? Okay? Huh? The grocery store just gave you the receipt for how much flew out at that moment. All right? Huh? You're keeping track of both. All right? This is the setup of Lagrangian mechanics. It is time. It has this combination of positions and velocities, and then it has this thing called a chart of accounts. All right? Okay. Now, how do you find which path you're actually taking? You need a little bit more. That's a Lagrangian, and then you need to do this minimization. We'll come to that in the next lecture. What I want to do here is just say, all right, this abstract setup is pretty clear, and I want to walk you through a bunch of examples to really ram that home. Okay? Huh? But we've already achieved a lot. We've taken a very abstract setting of differential geometry, and you can see how useful this is. Because had you done this with a lot of I's and Q's and all this stuff, the way they normally teach Lagrangian mechanics, you would have been lost, okay? Because you have to see it again and again and again and again, and then, huh? All right? And you also see how important it is to separate time and your accounting or your bookkeeping from the economic reality. You could have chosen another time, and we will do so later. All right? We'll start clocking events. Huh? And time will become another stock variable, and we can look at the price of time and that kind of stuff. Okay? So you're not stuck with this. They needed that for relativity, right? Because our clock time wasn't the right time. Huh? Okay? All right? And they needed this also for relativity because these spaces were not flat anymore. Einstein's spaces were hyperbolic, and then they had general relativity. It was all over the place, okay? So you had to separate the two. The reason it wasn't separated because everything was kind of flat. So you thought of a coordinate system and the space as being the same. And what people did is they chose handy coordinates as polar because we can do a pendulum, and that's what you learn, right? You get these different problems and you go and look at the different one to make it easier for yourself, blah, 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 blah. Huh? This is just saying, look, you got to start off first looking at the real problem and then choosing handy coordinates instead of going like, okay, huh? All right? So you deconfuse your head on this, okay? What's important is this is the only stuff that's truly economic. All the rest is just things you can change. And one of the problems they had in physics, and what you also see in a lot of economics, it's very hard to separate what assumptions were just thrown in to keep track of the bookkeeping, and what things are real, like in least squares. You kind of assume you already know your axes, and then you're going to square something and another square thing, and you add them. But had you chosen different coordinates, it would have a total different answer, Huh? Okay? So it all gets interwoven, and it's very hard to keep your reasoning pure and easy. It gets complicated, You need trick after trick. So I love this stuff. All right? It's the only way stupid people like me can get anywhere, because you just got to organize it, okay? Huh? All right. So is this okay? Are you guys okay with this? Huh? I see a lot of nods, so that's fine. Huh? Okay. So first example I'm going to give is that commodity example, where that space is as flat as a pancake. All right? Huh? Okay. So you'll have two commodities are a special type of good that are fungible. The stuff where Newtonian mechanics of demand is for, right? Just apples, pears, pork bellies, those things, not works of art, all very special stuff, okay? Huh? And then you could have, this will be your economic reality. So obviously I chose 2 here, right? And then I did make my chart of accounts like this, but normally you would just kind of put it on there, get it done with. But this does say you can change this, I can share this, makes no difference. This thing will just keep track of it, So I made the difference, but you see it's kind of, yeah. Okay, but okay. Let's just go through the exercise. So the degrees of freedom is the number of agents times the commodities. That's N times D. So in this case, it's 2. So what do we have? 1 agent, 2 commodities, or 2 agents, trading 1 commodity. Those are the 2 options here, right? Okay, nice and simple, but already 2 different things, okay? Then I just wanted to mention what these spaces are. So this is the stock space, the configuration space Q, right? And it's just R2. Okay, nice and simple. Then the tangent space, where all the demands are, happens to be also just R2. Okay. Now this is the notation they would use. This is stock space, and the Q is for configuration. Okay, but the C was taken, and the Q sounds like configuration. That's what everybody uses. I like it because it's the quantity, the amount, the stock amount. All right, where the little Q's live in the big Q space, right? Okay. Then the flows live in the tangent space. So that's the space of flow vectors at this point Q, any point Q, on the stock manifold. Okay, that's how you read this. So this means tangent space. This little q means at, stock Q, and this means in the stock space. All right? Okay. That's how you read this. So it's nice notation. And that also is R2, right? Of course, because you can only demand stuff for items that are there, right? And there are, say, 2 items, 1 agent, you can only use the same dimension, right? So if you have any type of manifold, the tangent space always has the same dimension as the manifold, right? Okay. Now, is that enough to describe everything that's happening? Well, the answer is no, because we need, for every stock position, we need a new tangent space. So we got to bundle all these ones together, okay? Is that clear? You can't do it with this one, because here is something completely different. There's a different space, okay? That space is attached here and not attached there. Now here it looks silly because you can say, well, of course it's attached here, but I'll just move it back, So you happen to be able to do that in Euclidean space, the flat space. But in general, you can't do that, okay? You can't just move these things back. If you're on Earth, your tangent space cannot just be moved back in one way. It depends completely if you go which way, how it's going to get oriented, all right? Okay? That tells you your problem. So if you assume you can get away with one tangent space, you already are excluding almost all interesting problems, okay? And it will all break down. It all breaks down at this problem that it's sometimes called a parallel connection in, or a connection in Riemannian geometry. Sometimes I think it's the theory of principal bundles, some kind of structure that you can move these things back. But if it's not there, it's not there, okay? It's okay. It's okay, we still move on, all right? And so you bundle these together, and then you drop this Q because it's at every Q, right? And then you have something that's called the tangent bundle, okay? And that is for us what we would call the state space, really, right? So it's a space. Say I have only one Q, here's a Q, and here I have all the V's, right? So rather than drawing them as tangent vector, I just have an extra axis where I put them, right? And here I have another V, right? Okay, and here I have another V. Huh? All these different copies of this. Okay, you see that? Huh? So it looks like there's some base space Q here, and at everywhere here, there is a tangent space, right? It's kind of sticking out like that. You could, here it doesn't stick out, but it lies flat on it. It doesn't really matter how you picture it, does it? Huh? All right. This is also why they call this a fiber, because they are like fibers sticking out. And this whole thing is called a fiber bundle. All right, so you bundle together all the fibers on the base of configuration space, okay? So you may encounter this type of terminology, you'll be super confused, but really it's they're good names, huh? All right? Is that clear? I see you.
Because you said more copies of the fibers, but in one V, you could also have like smaller V's, right? You don't have to have copies exactly the same V vector.
Well, here you have copies of planes. In one dimension, you'll have copies of lines on a line. Here you have copies of planes on a plane, and here you have copies of lines on a line.
The height of the lines could differ, right? So
yeah, but the size of the plane can also be different. I'm not saying what the values are. You're confusing the space with some value that might be in there. You see? Huh? So if you have a one-dimensional system, right, then what can the velocity be at this point? Well, it can be this, it could be this, right? It could be this. Huh? Now, all I'm doing is I'm taking this axis and I'm turning it around, right? Huh? And then it looks like a fiber, huh? Huh? But I could also think it's a fiber that's going parallel. No, it makes no difference. I can plot it like this. Now the point is, the thing only knows how to travel down and come back to where it was attached. You don't think of this as an angle or as something. As a Euclidean space. That's what's so confusing when we plot state space. We'll do here V, and we'll do here Q or something, and we'll write this vector Q, V like that, right? This is very confusing because you would think this is a 90-degree angle, but it's not. There's nothing to do with that. How is the velocity at 90 degrees with a stock or something? It is ridiculous. Now it isn't actually. It's more tangent to, You can't even be orthogonal to a point, and the stock is just a point. So don't think of this as being a Euclidean space. Think of this just as a way of representing all the fibers. Okay, so here are the stocks, and here are just all the flows. And this is, so if you have two dimensions, you'll have this, and then V1, V2. You could arrange them a little different, But you see how confusing this is compared to this picture, This is what you'll have to do in Newtonian mechanics. You'll just have to keep track of all these, and then you pair them up, and I don't know, You see? Okay? So don't confuse the size with the space. All we're doing is getting in the right space now. We haven't said how big these things are, okay? This is the trick. You can't do it all at once, because then you'll lose the mechanism for modeling, Then you only have, one solution, right? First, what space are we in? Okay, here we are. Where's the chair, right? And where's that chair? How fast is that chair moving? How fast is that? Could be anything, right? In principle. Okay? Now, just ask questions because, and never be ashamed, because it's all obvious, but it's just not so obvious that it's obvious, if you understand what I mean. So you've learned this all in a weird way, and then you somehow have to descramble everything and just get it, I just make peace with this is how it really is, all right? And let me just relax about it, and undo all the errors that built up in your brain that you were able to carry along and still pass those exams because it really didn't matter, right? Okay? You want to go to that pure, simple understanding that works for stupid people like me, all right? Okay? That's what I like about this stuff. You just build it up one on one, right? So if this is apples and this is pears, now what does it mean to have 90 degrees between apples and pears, What does it mean that the length of this vector is 5? Well, then we take apple squared and add it to pear squared. I mean, hell, or oranges. I should have taken oranges. You're just adding apples to oranges. No, even worse, you're adding squared apples to squared oranges and taking a square root. Now, you don't know. I mean, whereas we tell our children not to add apples to oranges, So what does this all mean, right? Aren't we making lots of mistakes by endowing these spaces with all the stuff that we're so familiar with, and then we build this mistaken model, and then somebody comes around and says, well, it's not working, Now, how do the units then work out? Oh, I don't know, Okay? So you got to undo yourself from all that luggage that you got going on there, to solve these really specialized problems where everything is always Euclidean, and every angle is, now measured in the same way, right? Except when you do large distances on Earth, then you have to make a correction. And accept and then learn all these exceptions. And never get anywhere. All right? Okay? So this is, what does this mean? It just says, well, this whole way of looking at it, the way we're doing it with Newtonian mechanics just fits right in. What's the benefits? You can argue but I did answer a few questions, and some of you are going, oh, okay. It helps you understand why that other stuff working and what the assumptions are that went in it, So you're already doing okay, although this looks trivial, right? Don't underestimate how well you're doing. By stripping away the, a lot of learning I found out at my age is unlearning things, okay? That's the hardest part, to undo what's in there and is wrong, okay? So the greats like Newton and Einstein, they just were capable of doing that. So Newton had to unlearn this Aristotelian mechanics where a force was required to keep up the motion, all right? And Einstein just had to unlearn this whole thing that time can be measured with a clock standing still, and a measuring rod always gives you the right distance, okay? A big step to take, but he did it, and he was able to go beyond these things. So it's difficult, but it's well worth your while. All right? So far, so good for commodities. Now, I got a few more slides. I think we can get through it. So then I go to something more interesting. This is a busy slide, and it's got 3 different types of things on it. So what I want to do is, where shall I begin with? Yeah, I'm going to begin with this one. Now, in analytical mechanics, Lagrangian mechanics, the normal way you get like non-trivial Lagrangians is to put on constraints. And what you do is you formulate these constraints in a bigger space. So here's a bigger space. This is not my Q's, right? Some bigger ambient space of products in capital, okay? I'm going to turn out to have only one Q, all right? So my degrees of freedom are only going to be 1. But I'm in this bigger space, okay? And what you do is you put on a constraint on that space. So here, if I have a pendulum, you all know that, then it lives in a bigger space. That's the plane. Actually, it lives in space. But let's say I'm holding it flat, and it's a plane. And then it can move only like this, right? So these are the x, and say call this k or something, k. an x, okay? All right? And then what are the different types of positions? How many dimensions does it have? Huh? 2? I would say 1. Only one angle is required to specify its position. So although it lives in this bigger space, we put on this constraint, right? Huh? That this distance has to be the same, huh? Okay? And that reduces the manifold to only 1, okay? Now what is this manifold then that it lives on? It's a circle, right? It lives on a circle, right? The tip of this thing, the bob, lives on a circle, doesn't live in a line, all right? Huh? So this is not a flat space, right? Now is a point on a circle, can that be a vector? What's the 0? Well, King Arthur will tell you there is none, right? There's no head of the table, right? There's none, so it's not a vector space. It makes no sense to add 2 points or multiply 1 point by something. It's all nonsense, okay? It's just a bunch of points living on a circle, okay? And when you turn around, you just come back to where you started, right? Okay? That's all, right? So you're going to have, if you live on this circle, which the bob of this pendulum does, you're going to have a one-dimensional manifold, right, of your configuration space, right? By the way, your tangent space will still be a line, and it will just be this line, and it will fly right off your configuration space. That's exactly what happens if you shoot with enough velocity, otherwise gravity will get you, but, you know, off. It will just go straight out in open space. You know, it won't stay on your configuration space again anymore. Huh? Okay? Right? But forget about that for a moment. Huh? So you have now a non-trivial configuration space. All right? Huh? Okay? This is not a difficult example. Huh? So, huh? And it's like problem number 2 after you do a mass spring system, right? You just do this one. And then I admit that what we typically do, after a while they get tired of it and they linearize it around this point and they say, there, it's almost like a line, and now I can treat it as a line, right? Huh? Okay, but it's only for very small, all right, okay? So there's a circle. Here's another one, and here I just fix this distance. So the ambient space is again 2, but now I get a line. So a subspace that's one-dimensional, but it looks like a line. That's fine. I knew how to deal with that. Here's a third one. This is a hyperbole. Now, the thing is constrained to stay on there, so that's also a one-dimensional space. It's certainly not flat, okay? All right? Okay? So these are 3 examples of constraint manifolds that I want to discuss right here, and I want to discuss their economic meaning. All right, to give you the idea of how important this type of analysis is. All right, so let's start with this guy right here. This is the pendulum. All right. You know what? Yeah, let's start with that. So, what is a good example? Now, I'll tell you what a good example is. That this is a banking example, and it's called amortization. So think of this as your capital, all right? You make some loan, all right? And then when you borrow money, or you loan money, say you loan money, all right, you get interest. Now, what is interest? Is that capital? No, it's something else. So this here will be your interest, okay? So this is your principal, that's the amount of the loan, and this is the interest you get, all right? Okay? Now, what happens when you have an annuity, right? Well, you first have to pay a little bit of interest, right? And then you have to pay off a little bit of that capital, right? That's called amortizing it, right? Say you have a mortgage. Then you pay a little bit less interest, and you pay off a little bit more capital, you know, and then you move like that. And that's specified in your contract, okay? So your contract, your mortgage contract, keeps you to this thing that I, for convenience now, plotted as a circle. All right? But you could deform it a bit, right? Okay? You're cool with that? Here, take another example. Suppose these are chickens. These are chickens. And these are eggs. So you got your chicken and you got no eggs. So then these chickens start laying eggs. But then some of these chickens, they get old by laying eggs. They die, right? And then you get less chicken and you get, you go on like that, right? So they start laying these eggs, and then here you have all eggs and 0 chickens, but 0 can be, this is typically what you see with these things, that 0 is not 0 chickens, it's like 1,000 chickens, and you see that herd, or what do you call it, flock, or kennel, or I don't know what you call them, or chickens. What do you call them of chickens? What do they live,
Like what, the group of chickens?
Yeah.
I'd say flock.
A flock of chickens. But in your, it sounds terrible. It's more birds flying.
Birds, right?
Yeah, but I think it's a roost or something. Is it a roost or something like that?
A group of owls is a parliament.
Huh?
A group of owls is a parliament.
A group of owls is a parliament. Now, but when these chicken farmers, they have that's their capital, whatever, right? And that thing starts varying between, some amount and another, because these eggs, they start hatching, and then, you get more chickens and less chickens, There's models for these things, okay? And they go like this. You also have these predator-prey models. So these are very old, where you have the Adriatic Sea, they had this. They have these predator fish and prey fish. So they start off with a whole bunch of prey fish. And predators, they start eating them, so they become less, and then the prey goes up, right? But then there's too much prey, and then they start dying, and then the whole thing goes in a circle all the time, right? You can think it through. I have a paper, I describe it a little bit better. Or you can see this as, I don't know, land. This is land I want to keep. Machines, and they wear off, and they do this, and then you got to rebuild your machine. I don't know. Use some of your proceeds to rebuild the machine, right? So this is a typical kind of, I call this capital, whether it's money or eggs or chickens, or you could have a beef farm, and you get these calves, and you sell them off, or you have them grow up, and then they replace. Predator-prey models work like this. Okay. So this ecosystem, how many dimensions does it have? It's going to have one dimension, right? So it's just some kind of total size, right? Okay. And then, where you are in the cycle, right? These things go in a cycle, right? Where they produce and then reborn, and then, so it's just whatever cycle these guys are on, right? Okay. So in that cycle, that's the phase. The word phase is actually a nice word in this context. So the phase, your chicken coop, is, I think it's a coop, right? Yeah, it's a coop, yeah. It just flops out when you don't think about it. So it's the phase of your chicken coop. Where are you on your chicken-egg combination, All right? Now that phase is, that's the only thing you need to report, because this is a fixed number. So the only thing that's dynamic here is the phase of your of your mortgage. Is it totally paid off? How far are you into your mortgage, right? Have you started your mortgage, right? You have a 30 years, so this is going to take 30 years, right? And then you can measure that, the phase. Okay? Okay? So this is a non-trivial manifold, right? Nice and round, one-dimensional. And you map it into just one number, and this is sort of you could call the total yield, right? So it's some kind of phase, okay? I don't like the word yield, I put it there, but it's the total yield. I'll leave it here. I had all kinds of reasons for calling it yield, because you have some negative yield on your capital and positive yield on this thing, It's some kind of total yield. If you just use the phase definition of what's going on, you have the right thing. So how do you calculate that? Well, you look at where you are. It's the same as this angle. Basically, it's this angle, right? Okay. I think I made a mistake here. This is only valid for that one. I have to, yeah, this is not right. I'll have to fix this. Here's, you can calculate the angle. Okay. All right? That's the right units, right? So if this is interest and this is this, then this angle is dimensionless. And then the angular velocity will be the derivative. That's in percent per time or something. That's the right. It's the interest rate, right? Okay. All right. So these capital theories, they give you these kind of rotational things. Okay. And you can see that this Q doesn't have to have units of items. It could be just a percentage, or a degree radians. So many radians in your production cycle. All right? Okay. And then the derivative is like an interest rate or a yield rate. Okay. You see how general this theory is? If you would do this Newtonian, you'll be struggling because you will have this pendulum, and you've got to define this and do that, and then come up with all this machinery, then calculate angular momentum, right? A whole new theory. And that's what they did. So when Newton was done, Euler had to come up with this theory of rotations, completely separate. Ultimately, you could derive one from the other, but there was no way of attacking these problems in a just general setting. That's what this does for you. So the normal economic engineering, I would first do commodities, and then I would do capital return, and this, and another fun application, and another fun one, and then you build out your inventory, your fun applications, and you're never done, right? This is quite different. Let's look at them all from the same perspective. Okay? So this is sometimes called the holonomic constraint, right? So if you're doing this amortizing kind of thing, then this is your constraint. So you have this ambient space, and then you say, I put on this constraint. So you have a two-dimensional space. One constraint brings you to one-dimensional manifold. And we'll choose the angle here as the Q, right? Which is the total yield. Okay? All right? Done. We can look at other things other than circles. Like here I have a different type. This is what you use when this is land, right? Now one of the things you may know in economic theory is land cannot disappear or come. Land is always land, unlike a machine. So it's a form of capital that is entirely inelastic or something like that. I don't know what economists say. The whole idea is it's fixed, right? All right, it's special about land. There's some other ones, but I can't even remember. Well, they have other ones like cigarettes or gasoline, but I don't see those as fixed in the same way land is fixed. There just is no more, right? The other ones are just fixed because the price elasticity is really high or low. This is just built in kinematically. It's different, all right? But it's hard for them to see the difference between kinematics and dynamics, so it's hard for them to unravel this. This is just a submanifold. And this is one of the strengths of Lagrangian mechanics, that you build in what submanifold you're on, so you don't have to later go cancel your x's and y's like you were going to do, right? You start off on the right space, okay? Here's land, so it's constant. And what's the yield from land? I don't know, your crop, so many seeds or something, or so much, or so much, this grain you get out of it, right? That's the oldest form of capital was land. It was somewhere in Sumeria 10,000 years ago. Some dude figured out to take a thing of grass, where you have these little seeds, and then make really big ones in the valley of I think it's the Euphrates or the Tigris, where they come together. And then they made the first farm, and instead of hunting, they just started eating that stuff, making bread out of it, and then they started eating that, okay? And then all of a sudden, you had these two different types of goods, right? You had capital goods and the production, and they were different. You couldn't eat the land, and before land was kind of useless. You just roamed around, and you started hunting or gathering, and who cared? Why do you need to own it, right? Huh? But then it becomes a good, but it's not the same. Huh? It's a separate kind of thing. You can't eat it, but you can eat the product. That's the idea. So these things come with a product. So you see this high idea of an ambient space coming. Huh? And then you can also do this division. And then it's a little more complicated because here, this angle is still defined. It's just this divided by that, right? Huh? And but it will be like bushels divided by hectares. Well, it's not dimensionless. You can do the whole analysis like that, or you can just say, well, and they do this. They call that the reseed ratio. So they don't measure land in hectares, but they measure land and how much seeds equivalent is to put in there, right? It's called the reseed ratio between, and this thing is called the reseed ratio. So you measure land and the amount of seeds you could plant, and this is how much you're getting out of it, right? And then it becomes dimensionless number, and that's called the yield, all right? So they play exactly the same trick that we play with angles they do. They don't call it an angle, right, mind you. They don't have this picture, but they use something we can translate geometrically into this. This is all about how you could do geometry with these things. Mind you, the Rabobank, where we did this for, they never thought of it this way. They was on a table, and the guy couldn't believe it. He says, wow, and he starts drawing these things. These are these diagrams, and he said, wow, I got a real space, I got a rotation, right? It was just enlightening for him. He could get rid of all of his graphs and just put it in one little movement like this on a mortgage, now. Okay? So this is kind of easy. This is the easiest. I started, but again, it's a constraint. K is R, X can be anything, right? And you got a submanifold. This one happens to be a line. Huh? No problem. Okay? There's a third one I did. This is a hyperbola. This is something you would call growth. We would call this a rotation. We'll call this a shear, right? So you're shearing this thing, and this one, if you have less land, you get some shearing motion here. This we call a rotation. I'll talk a little bit later how it relates to group theory, okay? And this thing we call a boost. So you shear along, you go whoop, all right, along a hyperbola. Now, how does that arise? Start first with an example of a savings account. Let's take a savings account at your bank. So what do? You put in an amount R on your savings account, right? So far, so good, right? Maybe you guys have never done that since you have no money, but so later on when you earn something, you'll end up doing that. Then if you're lucky, so this is what you do. You do this, boom. Then if you're lucky, you get some interest, boom. All right? Then what they do in a savings account, they'll compound it into the savings. So they don't give you the savings, they'll turn it right in, right? So boom. Okay? And then you'll get interest on more savings, boom. And then they'll put that in your savings account, boom. All right? Whoop, 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 and you take off like a bandit. All right? You see that? If you figure out what that is, you have the ratios not to a little easier. It's like the ratios here. If you choose them right, it's a hyperbola, right? Okay? You can see how it becomes up high. It's just the opposite of this thing. This thing, somebody dies and goes away. Here, you get something and you add it to it. So it's any type of growth works this way. If you have a population and nobody dies, that's how the population grows. Now, people die, but there are more people being born, then you get a net effect this way, and then it will start growing. Huh? This is replacement level, right? And this is when it's shrinking. Huh? Okay? Huh? All right? This is all compounding. This is it's kind of interesting. This one is what you really would think of as compounding, right? Huh? Because what is it? It's e to the power of whatever your interest rate is times t. That's how much you're going to end up, right? If you follow this hyperbola. And that's true because that's equal to the hyperbolic cosine plus the hyperbolic sine, right? Huh? This happens to be the case. Huh? So that's a growth. But this thing is also a kind of accounting, a kind of compounding, because this point is e to the I omega t, right? Huh? Where omega is q dot. Huh? All right? Huh? Well, you know that, huh? Because that's cosine omega t plus I sine omega t. So if you think of this as the complex plane, you know, you'll see the resemblance, you know. So this is like exponential growth, but this is like exponential, also an exponential movement, right? Huh? Okay. It's also sort of compounding. It's just kind of seasonal compounding or circular or cyclical compounding, you could call it, right? So rather than compounding into the future, you compound in these cycles, or any trader or manufacturer or a grower would do. Huh? So you whoop, 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 whoop. Huh? Now I got tomatoes, now I have no tomatoes. Now I got tomatoes, now I need seeds. No, huh? Okay? Huh? All right, so interesting how it, you can view this also as an exponential. We'll talk about all this stuff. And instead of I, you use some number epsilon here, so that epsilon squared is 0. Huh? So if you work out the Taylor series, you'll see you'll retain only, you'll have r plus this term. Huh? Okay. Here you need to know that I squared is -1, otherwise you go the wrong way. Right? Huh? You go that way. Here you could actually put a j, and then j squared is 1 because you're going along that way. So this is either I, so no, j. And you can use these different types of complex numbers. I'm only saying this because you guys are so used to using complex numbers for rotations, but you can also use them for all these other motions, all right? And later on we'll see how we can use matrix Lie groups to kind of super generalize this idea of return, and compounding, all right? Yeah? It all makes sense when you consider the manifolds and Lagrangian, it all becomes easy, it all comes together. Who would have ever thought of that, right? If you've just been plug and chugging. Okay? I told you it's a beautiful theory. I'm writing this up in a paper, so there'll be more details. But you guys are satisfied with this explanation for now? Huh? This is a tough crowd, so I'm happy about that. Huh? Let's move on. Huh? So yeah, here, I already did it. So we can generalize this picture a little further. You say, that sucks, only one manifold, right? I mean, I need more. You can have more products, if you have, I don't know, chicken, you can sell meats and you can sell eggs, so have 2 products, and a lot of things. So you can have 2 forms of capital with 1 product, and, you can get very complicated combinations, right? And then you see these movements, they become more and more and more complicated, all right? And they become very complicated manifolds. And what we do is rather than describe them like this, and other one separately, we have a name for all these, and they're called Lie groups, okay? So Lie groups are things that are operations, so you can produce something, but at the same time, it's a manifold, nice and round structure, all right? Huh? Okay? Now, this guy here is a manifold called SO2, special orthogonal group on 2 dimensions, because there are 2 dimensions here. the orthogonal group just means that this is, always orthogonal. And special means that it's not changing the length. Okay? An orthogonal matrix is one who, who is self-adjoint, blah, blah, blah. It don't matter. It's like a rotation matrix is a special orthogonal. Is a orthogonal matrix because it's self-adjoint. It times its adjoint or transpose equals 1, right? Yeah, because the transpose rotates you back, right? So you get the rotation, and the transpose rotates you back, so you go back to the identity. All right? So that's why it's called an orthogonal matrix, I suppose. And special because you're preserving this thing. All right? Now, what do you get in higher dimension? You get something, whoopity-doo, it's called SO3, right? So SO3 lives in an ambient space of 3 dimensions, and it has 3 dimensions, right? So you can do 3 rotations. It's kind of funny because you can do only 1 rotation in 2 dimension, right? But in 3 dimensions, you have 3. You get 2 more because you're really counting planes, right? So there's only 1 plane in 2 dimension. You rotated a plane, so you're counting 3 planes. So this is the economic meaning. So every plane is a capital product combination, right? So in 3 dimensions, you can just make 3 of those combinations, So you can trade one form of capital for another, or all right? So it gets very complicated because these are non-commutative groups, So you can go from one way and another, and you won't end up at the same position you were. That's not the case on SO2, right? You can go here, you can go back, and you can go. It doesn't matter, all right? But on SO3, it does. If I take this thing and I rotate it like this and then like that, or I do the other way around, I get something else. And that's going to be the case with somebody dealing with his cap. If you have 2 forms of capital, what are you using first? Are you first using the shovels and then the land, or the people and then the land, or is for the land and then the people? And blah, 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 blah. You have to get the order right. Otherwise, you get ridiculous things. Okay? It's like when you drive a car, you got to get the order right. Okay? If you walk, you can go up and you go then to the right, or you can first go to the right and then go up. Why? Because those are commutative, translations are commutative, right? But if you drive, you have a translation, so you can press your pedal and go forward, or backward if you put it in reverse, and steer, right? Those are not commutative. You can't change the order. Because if you could stand in your parking spot and first get all the steering out of the way, and then just go press your gas pedal, right? Or, It doesn't work that way. You have to get the order exactly right, okay? Otherwise, you take something completely different. You're going to end up somewhere completely different. If you first get the steering out of the way and then you press the gas, you're going to end up where the car crash. You see? Okay. All right. With a car, you can also go sideways. So you're going to steer this, but you can't have a sideways thing, but you can compose it by, all right? So that's how you park. So these things get really complicated, okay? So this group structure, this manifold structure is very important, to keep track of in order to know what's going on economically, all right? Okay? Now there's also groups that have this group here is called SO11. I'm not sure if it has a special name other than SL11. And that generalizes to SO21. These are used in relativity. So relativity, you can kind of rotate in space, and you can also do something in time, and that goes hyperbolically. All right? And this is the time dimension. And these really are your space dimensions. Okay? So these are other groups. I think these are called the Minkowski group or something, or not the Lorentz group, but the Yeah, it's the Lorentz group. It's the, I think this is the related to the Lorentz group. These groups have very different names depending on what representation you use. Okay, huh? But they're all homeomorphic, as they're called. All right, huh? Okay. Okay. Just to see that this is not a trivial business. Once you go out of one dimension, in one dimension everything is easy. In two dimensions, it's like driving your car. You're in two dimensions with a non-commutative thing. It's not so easy. Not everybody can park, huh? Double park, So, I wanted to give you one more example. 2 more examples, and then this. We won't have time to go through it, so let me leave this then for next time, because it's almost time. I think it's good to keep this here. So where did we go? Well, we started off giving this whole picture of what the ingredients are, and I've been talking about special cases for these, right? And what these, and later on I'll tell you what flow spaces belong to it, and then we'll go and finally do some dynamics on it, right? But I think it's important first to realize that this is just not merely a mathematical exercise, that we need this machinery, to describe these stock spaces that can be quite complex, okay? All right? So a lot of these things look like the rotation group. All of Lie group theory is a little bit like the rotation group. And what's great about the rotation group is they all can be parametrized with something that's like an angle, which is like a return or a yield, some dimensionless number, and whose rate is then like an interest rate or a this or a that. And it's a very natural way of talking. So economic growth is always seen as exponential growth, okay? So it has to be on a hyperbola, otherwise you cannot get an exponential, all right? Huh? Because the exponent is the sum of the cosh and the sinh. This is just how it is. It's just a decomposition of the exponential, all right? If you look at 2 dimensions, okay? So there's the growth of capital, and then the growth of how much interest you received, huh? Okay? So what I was going to say, yeah, so this is a very natural cue to use, all right, in economics just as it is in engineering, right? I think in economics more, everybody works with ratios and percentages, because they hate units, these guys, because their units never correspond, right? So the only way to know how to make sense out of it is to go to unitless quantity. So they divide income by something else, something that's constant, so, and they divide this by a constant, and they'll talk about real and nominal inflation, because the constant they're dividing by is not the current constant, and all of these can be seen in terms of some kind of compounding of, this is also called the exponential map, the compounding. And it's defined for any Lie group, even wider, or for any Riemannian manifold, I believe, right? So it just gives us, it sounds all like very fancy stuff, but it gives us a very, very nice picture to treat these things very uniformly. And also you can impress your friends and your committee, if you talk about that, because it's one of those things that everybody, nobody knows what it is, but everybody knows they should know what it is. Now, those are the things that do very well on a final exam, all right, with the committee. Huh? Okay, huh? So, huh? Okay, so you also get a little bit of that, all right? Huh? So then, so next time we'll finish this. We'll look at these projective spaces. I also want to look at a little broader thing. It's like the Euclidean group. And that's when, this thing is now just turning, but suppose you're making a little, get a little extra eggs every time that you can just cream off, right? Extra cream that you can cream off. Suppose these are cows and this is milk. And well, you want to cream off that milk, right? So you're creaming off the milk. So actually the rotation point is moving up, right? okay? You can also move this way if you're adding some stuff to your flock, right? Or your coop or whatever. So you'll be rotating, but you're also moving, right? So this is what you would call your earnings or your capital accumulation. That's the translational movement, right? Eh? And this is your business. I'm in business. I'm rotating, okay? So you compose those two moments and you get a bigger group that's three-dimensional in this ambient space. And that's called the Euclidean group, because the Euclidean group, that's all translations and rotations, okay? That's the group we're always familiar with. That's the group that's assumed in Newtonian mechanics, okay? And in three dimension, it gets more complicated. It's the three-dimensional recalculation, three and then three rotations, okay? 6 dimensions all of a sudden, right? Now you don't have to rotate, you can also boost, okay? That's called the inhomogeneous special orthogonal group, and that's also called the Lorentz group. Yeah? That's the big group of general relativity, all right? Huh? So that's these manifolds. They correspond to those. These are, again, these are projective spaces. We'll come to that later, okay? And when I mean later, that's in this little application, all right? So it's a wild ride, but it's going to be a fun ride. Okay, see you next week.